Hi everyone. My name is Amar Prakash Arad. I am a research scientist at IBM Research Bangalore. I'll be talking to you today about deep domain adaptation under label scarcity. Uh, Before we dive into domain adaptation, deep learning has been very much successful due to one of the most common supervised learning algorithms, which requires large amount of data. Uh, and has been very much successful in almost all the areas where it has been applied, such as NLP or images. But one of the problems which we always face with such models that these models do not generalize very well to a new domain, unlike human does. For example, if those are trained on some of the normal roadside views for object detection of different things, it may not be doing great with very snowy kind of roads. So the question domain adaptation basically talks about is how to predict in a new domain. Uh, um, and and that more formally, actually, we can see if the model is trained on let's say bicycle dataset for visual domain from Amazon review, that model may not be doing great if you have a bicycle images from different data sets such as for robotics. And this is mainly because you see some distribution shift across domains. Similarly, in textual domains, let's say you train a model on book reviews text, may not be doing great with appliances review text. So these kind of problems has been dealt in domain adaptation. We will be talking one step further to it. What if the training data in source domain also, where you are actually training, that also has scarce labels. Let's set up the background more formally. Consider classification task where X is the input space and Y is the label set. And the source domain can be composed of, or can be viewed as composed of Xi and Yi of all examples, which actually form the distribution Px's. And similarly in target domain where we don't have labels and you want to predict upon the data set what you have Xi. And the distribution actually is composed from the X's, which we call it Pxt. So learning in source domain basically aims at maximizing Py given your input data X's, whereas in target domain we aim at maximizing Pyt, but given your X's or which is actually trained on X's. So this is the key learning what we always talk about domain adaptation. The goal of learning algorithm in domain adaptation is basically to build a classifier that runs a lower target risk. Or in some sense, what we're saying is that under your target data distribution, your hypothesis is doing have a minimum amount of failures. One of the very important concepts which we all talk about in domain adaptation is covariate shift. Covariate shift basically talks about the dissimilarity in only marginals of source and target domain data, not the conditionals, which we often actually do for labeling. So more precisely, Pxs is not equal to Pxt, but Ps y given x is equal to Pt y given x. And under such conditions, if we have a means to basically minimize the discrepancy P margin of marginals, we should be able to use that model to be able to predict in target domain despite not having labels. And most of our DA work actually aims at minimizing the domain discrepancy by aligning the domains under covariate shift assumption, what we just talked about. But if you don't have enough data even in source domain, then your estimate of PYS given X that itself becomes weaker. And we'll be seeing that how to improve upon even that. So typically in domain adaptation for deep learning networks, where actually you expect to fetch data sets, data from source domain, which is access going to for a few layers of deep models. The first few layers basically extracts features and that projects onto the feature space F. So basically, the input domain data or source domain data basically is projected onto the feature space, which is then actually on the next subsequent few layers are projected on the label space to predict the labels. And this the feature extractor is it's generated by GF, and the label predictor part basically denoted by GY. So when trained on source only, the feature distribution do not match well with the target distribution, and that can be viewed at the feature space level. And in one of the very nice paper by Gann and Lemtsky, which is also called DAN, where they have used adversarial learning approach to basically minimize this domain mismatch at feature space level. How do they do this? To do that, they have used adversarial learning approach. And basically what they do in adversarial learning is they add another loss that maximizes the domain confusion in feature space, and which in turns induces common features in through the feature extractor piece of the model. What they do basically is they add a domain classifier, which you can see in the bottom branch. The domain classifier aims at discriminating between domains, but the gradient reversal basically reverses that the learned part, and the reversal basically induces the feature extractor part to learn only common features across that, and that way the feature space is indiscriminate between source and target domain. So in some sense, until the feature space, you are actually able not the model is not able to distinguish between source and target domain, and that also pushes the model towards, in some sense, situation where if the model is learned well with the source domain, should be able to do good with the target domain, and that is what we just talked about. That another covariance shift, your marginals are good, marginals discrepancies are minimized, so you should be able to do the level predictions well. And that can be seen very easily in the loss function. If you look at loss function, the first part is basically the label prediction or normal label loss, what you can say. And the bottom part is basically a domain classification, but reversed with a minus lambda, and which actually in turns is what it does is that the model minimizes on the label loss, but maximizes at the domain domain confusion. So basically, the domain classification part, which is actually done by theta d, is try to maximize the loss of that part, and this is a kind of minimax approach, and the model try to find a saddle point. So that way, actually, the model does very well if you have source domain data available, but you don't have target domain data, and the data are aligned in both domains, and that's a nice prediction for the target domain as well. But yet, and the DAM requires large amount of label data in source domain. The question here is that how do we even learn when you have a target domain data also in scarce? The source domain data also in scarce. So our approach is we call it traverse, which is basically inspired from both transductive learning and adversarial learning. We exploit the corpus data, which is unlabeled data, through adversarial learning. Just now we talked about, but that is fused with transductive learning approach, where we actually improve upon the level predictions in an iterative manner, even from unlabeled data. And that way, actually, we do not need to depend only on source domain data. We actually also exploit target domain data, which is yet unlabeled. So the key points here is that an adversarial learning approach, which we used to basically align the domains, and that alignment basically helps us also to reduce the domain adaptation problem to a semi-supervised learning problem under some mild conditions. And then on top of that, we actually do something which is very much inspired by constructive learning. We do interim target level assignment iteratively to improve the target predictions and also train the model along with. So if you look at our architecture, basically it is composed of two parts. The gray part is nothing but what we have just seen in Dan, which actually does the adversarial learning part of our model, and the upper part which does the interim level assignments on uh, on the aligned the domain at that level and in an iterative manner. So that is basically transductive learning part, and this we actually keep repeating iteratively for some time. This transductive learning, of course, is has been inspired by one of the alignment paper by Joy Chim and in 1999. Let's be a little bit more precise about that. In adversarial learning, which requires large amount of label data, but traverse does not require a large amount of data even in source domain. Uh, the traverse approach basically does learning in an iterative manner. We begin with a cold start by having random assignment of labels, and then we do adversarial learning on top of that. So basically, we initialize unknown levels with cold start and cold start levels prediction and update it through interim level and repeat this process with increasing level weights till interim assignment process saturates or converges. So that can be viewed by the loss function, what we actually come out for the traverse. If you look at the loss function, basically the first top, let's first see the bottom part. Bottom part is the domain confusion loss, which we have seen similar like Dan, because that has been inspired, that has been directly taken from a adversarial learning approach. But the upper part basically is slightly different. And what we see here is that the first part of the first part basically is the level prediction loss for the source domain, along with uh, the importance weight CL. And the second part is basically the level prediction loss even in a target domain, which has been assigned through interim level assignments. So this is that's differentiation basically comes because of the transductive approach, what we have actually leveraged here. And uh, because of the adversarial part being here, we still find saddle point through through this, but the saddle point problem is slightly different than Dan. Basically, traverse saddle point problem becomes a combinatorial problem as we see here, as it involves finding YJT along with, and hence cannot be solved as an adversarial learning approach. So we had to resort into a local search approach to solve the problem in an iterative manner. Uh, the local search approach basically what it does is basically it starts, as I just explained, it starts with a cold start. We start with the random assignment of labels of unlabeled data, but going forward, basically it invokes interim assignments, and after doing assignments, it's basically run Dan again to let the model align across the domains, and then again does the assignments, interim level assignments in an iterative manner. That process keeps repeating until the importance with what you actually see you that converges. Uh, that is that at a high level. Let's just quickly go into the experimental setting. We have done the experiments on both NLP and images for our model traverse. In NLP, we have looked into Amazon dataset where the baseline was nothing but Dan. And under the reduced supply of labels, we have looked into traverse, which is over Dan. And we can clearly see here that the model improves in most of the cases across the domains. We have also run through images using MNIST dataset, and there also we see that model shows improvement in most of the cases. The takeaway from here is that the traverse shows improvement with the state-of-art adversarial learning approach, even when the source level is in scarce for over 70% cases. And and such models does good for both NLP and images. Um, and thanks a lot for listening to us. And I'll be open to have questions during the online session.